Hey Ruby, I went to go give you a text about Fidianga and realized that I actually had never replied to your request for the question on the maths, and I feel really bad, but um, I said that I was going to have a look at it, and then I must have just completely forgot about it because when I went to text you, saw that the message was still there, so I'll have a crack at helping you out now. But I'm well aware that I've probably missed the boat there, and you've probably already done your exam. So hopefully it's not too late, and hopefully this does actually help. But anyway, there's a fair bit of maths going on. I'll try and condense a fair few year 11 and 12 topics into a little video, and hope that it still makes sense. But there is actually a fair bit of maths going on here. So bear with me. So on the right hand side, this unit is radians, and radians is a measure for degrees. Sorry, not for degrees, but for angles. And we typically use degrees when we measure angles. However, radians is mathematicians prefer radians because it's not tied to being within 360 degrees. We really can have an infinite decimal values for radians. So we can start at zero, go to infinity, whereas degrees is sort of tied to being within zero and 360 degrees. So radians is just sort of preferred. But in terms of what radians actually is, well, in order to figure that out, well, I've got a few scribbles here. As you can see, um, theta, the symbol that we use for unknown angles, has to be within 0 and 360 degrees. So we prefer radians because radians can be anything. It's just better for maths. So in order to get what a radian is, we need to understand the circumference of a circle. Now, the circumference of a circle formula, you may remember, is circumference is equal to 2 pi r, with r being the radius. The radius, half the diameter from the center of the circle to the outside of the circle. Now, if you were to take one of these radii and wrap it around the circle, how many do you think we would be able to fit all the way around? Well, a lot of people guess 6 or 7. That's a good guess because it's actually 2 pi. And that comes from the formula there. So 2 pi of the radii will fit around a circumference. And that's actually what we can define as a radian. A radian is I suppose, the ratio of circumference and how many radii you can fit. So we actually get 57 degrees, um, approximately. So 1 radian is about equal to 57 degrees. Now, we just need to understand that in order to understand why this unit is radians. Now we can start to think about, so let's read through what it says. It's plotted in radians as the arcsine transformation. Now, arcsine is inverse of sine. So not only are we're needing to understand radians, but we also need to talk about trig as well. So trig, might remember from year 9, SOHCAHTOA, got sine, cos, and tan. Arcsine is the inverse of sine. So the sine ratio or sine of theta is equal to opposite over hypotenuse from any right-angled triangle. Sorry, I should state that that is a right angle there. So opposite over hypotenuse. Doesn't matter how big this triangle is, as long as theta is consistent, the ratio is going to be consistent as well, and it's equal to sine of that angle. Now, that's all well and good if we're solving for side lengths, but if we want to solve for the degrees, then we need to do the inverse of sine or the arcsine, which will sort of reverse the process of trig and figure out what the angle is. And that's kind of what we have to do here, except they've made it a little bit trickier because they've taken a percentage and they've used percentage as a standardized score. And using percentage as a standardized score, meaning instead of writing it as a percentage, it's as a decimal. So the percentage naturally has to be between 0 for 0% and 1 for 100%. So it's in a decimal range between 0 and 1. So the standardized score, or Z score, is a term that's used in year 12 statistics. I'm sure you use Z scores in your statistics course as well. So the Z score has to be between 0 and 1. Now the arcsine transformation as it's used in ecology. I did have to get this off of an ecology website. However, it's the same as what we do in maths. I mean, we're using the arcsine here, the sine to the -1 of the standardized score, to sort of reverse engineer to figure out what the angle would be. So the Z score is essentially the ratio. And then we use the sine to the -1 or the arcsine transformation of that in order to figure out what the angle is. So you can almost think that the Y is your theta, and here's your sine -1, and the Z score is actually your opposite over hypotenuse. Now, again, it's further complicated because we have to understand actually a little bit of trig functions as well. Because when we're going around a circle, if that circle had a radius of 1, that's what we call a unit circle. If the unit circle had a radius of 1, that means that you could draw a triangle anywhere along here and it would still have a radius of 1. And you could, from that triangle, draw a vertical line down to the x-axis and create a right-angled triangle. So here, we've got a right-angled triangle on the unit circle, which in turn has a hypotenuse of 1. It's always going to have a hypotenuse of 1. Now, if that's the case, we can use our SOHCAHTOA from up here. So sine of theta is equal to opposite over hypotenuse, cos of theta is equal to adjacent over hypotenuse, and tan of theta is equal to opposite over adjacent. And we sub in into this unit circle. So sine of theta is equal to opposite over hypotenuse, but the hypotenuse happens to be 1 because it's a unit circle. So if we were solving for the opposite, it would just be 1 times sine of theta. So really, sine of theta is equal to the opposite. So if this is the opposite, this is like your change in y. You've gone from a y of 0 to here, which is your change in y. And if we map that across, it's probably about a half. If that was 30 degrees, it would be a half. And similarly, if we did cos of theta, it would be adjacent over hypotenuse. And the hypotenuse in this case is still 1. So because it's a unit circle. So 1 times cos of theta equals adjacent. So the adjacent can be mapped by cos of theta. So what that means is no matter what the theta is, if we've got a unit circle, the change in x, or the horizontal displacement, is going to be equal to cos of whatever that theta is. And similarly, the change in y, the vertical displacement, is going to be equal to whatever sine of whatever that angle is. So sine of theta equals the change in y, I've written down here. And cos of theta equals the change in x. Now note that this only works for x values between, sorry, I shouldn't really say x, it's more accurately, I suppose that works as well, but what I'm trying to say here is that it only works when we've got a hypotenuse of 1, because that's the only way that we could say that the adjacent was equal to cos of theta. That's the only way that we could say that the opposite was equal to sine of theta. So for all of these purposes, we're using the unit circle to sort of help us out a bit. So why is that useful? Well, if we start here, this is our 0. So if theta is 0, our sine of theta, or our vertical displacement, is 0. And as we go up, sure, 30 degrees, our sine of theta is a half. And as we go up, let's say 60 degrees, it's going to be about 0.87 up here. And then as we get to 90 degrees, we've got a 90-degree angle here now. We've now got a vertical displacement of 1. We've gone from 0 to 1. But remember, we want radians. So 90 degrees isn't actually quite that useful to us. We want it to be in terms of radians. And we said that there's 2 pi radians in a circumference, because 2 pi r is the formula for circumference. So how many radians are there in 90 degrees? Well, there's pi on 2, because there's 2 pi and 360 degrees. There's pi radians at 180 degrees, and at 90 degrees, we've got pi on 2. This might seem like it's way too much information, but it's actually quite necessary in order to understand why this only goes up to this amount on the scale. Because we go from 0, which makes sense, because if you've got a theta of 0, you're going to get a score of 0 as well. Like down here. Theta of 0, your sine of theta is going to be 0. And if you've got a theta of 90 degrees or pi on 2, which is the radian equivalent of 90 degrees, if your radian is pi on 2, you're going to get a sine of theta equaling to 1. So 1 is our maximum score for percentage. Our Z score, if our Z score is 1, that means that we've got 100% cover over here. So 100% cover, if you reverse that, so if you use the Arcsine transformation, which essentially turns the percentage into an angle in radians, the maximum score is pi on 2, because you've gone from 1, which is essentially 90 degrees, or pi on 2. Now remember that pi is 3.141592, whatever. It's a massive number that goes on forever. So if we divide that by 2, it's going to be about 1.55, whatever it happens to be. Not that necessary to actually understand exactly what it is, but we can see how this only goes up to 1.4, maybe a little bit higher. That's actually going to be pi on 2 because of what the radians are for 90 degrees. 90 degrees is the point at which we achieve 1, and we're going between 0 and 1 because that's what our percentage entails. That's what we have to go between. We're going between 0 and 1, which means we're going between 0 as an angle in radians and pi on 2 as an angle in radians as well. So here it says that it's back transformed percentage scale shown on the left-hand side. So we're essentially taking the percentage scale, back transforming it into an angle. Why? I don't know, but that's what they wanted to do. So I'm just explaining how it works, not necessarily why they did it. But it's essentially saying that back transformed percentage scale means expressing the percentage as an angle between 0 and pi on 2 radians. All right. I think that's most of what I needed to say. I hope that made sense. If it didn't, obviously there's a lot of content that I just tried to rush through that takes months for year 11s and 12s to understand. So if there's any other questions you have, please send them through. I'm so sorry I missed those last ones. And I'm excited to talk to you about Whitianga and because I'm going there in a couple of weeks. So hopefully this helps, and hopefully it's not too past the due date. All right. Cheers. I'll end this now if I can figure out how.